Hi, welcome back to Educator.com. Today we're going to talk about word problems. This lesson's going to tackle solving those dreaded word problems. Hopefully when this lesson's over, you're going to dread them a little less. We're going to start off by talking about why we should care about them, and tangentially, why we should care about learning in general. Then we're going to go over a general structure for approaching and solving word problems, and really any form of problem. We'll see how it applies to what we're working on now, and then we're going to understand, once we understand that method, we'll see a variety of different tips and strategies to help us get the most about it. So we'll go over some specific tips that apply to that general strategy that we talked about. And then finally, we'll work a bunch of examples where we'll actually see directly how we're using this step-by-step strategy so we can see how the method gets applied on real word problems. All right, let's go. First off, what is a word problem? The term word problem gets thrown around a lot, and it's pretty much just a catch-all. It's for any problem that's primarily being described with words as opposed to math symbols. So that doesn't mean very much, right? You can use words to describe a lot of things, so it means that there's no one way to approach word problems because you can be talking about so many different kinds of problems. Since there are so many different possible problems, we have to be ready to adapt when we're working on a word problem. It'd be like trying to answer the question, trying to figure out the one way to solve word problems. It'd be like saying, how do you play sports? There's a lot of different sports. There's a lot of different ways to play within each of those sports. It depends on the specific situation. That's going to tell us what we have to do. So the best method depends on our specific situation. So there's no one way to do all word problems. But we do know this one fact: pretty much all word problems are going to require us to think. We have to pay attention and be creative because we're being asked to do more than just follow a formula, as opposed to a lot of problems that we'll get in math where it's just like, here is the method that we do it, let's apply that method 100 times in a row, right? It's going to be understand this idea and then do some critical thinking about it. So we have to actually be thinking and paying attention when we're working on word problems. We should always be thinking and we should always be paying attention when we're doing everything in life. But for word problems, it's going to be especially important that we're really thinking about what we're doing and we're trying to understand it. So otherwise, it's just not going to click. Why are they so hard? Why are people constantly thinking that word problems are the hardest kind out there? Well, first off, there is no simple formula for them, right? There's no one way that you do it. You don't just plug things into it because each word problem can be different. So when we're working non-word problems, we normally have examples that we can follow step by step. There's some formulaic method that we can just rely on. But with a word problem, there is no such formulaic method. It's up to us to be paying attention, to be ready to be creative and thoughtful. So the fact that it actually requires thought, it requires some creativity, that's one of the reasons why word problems are generally harder than their non-word problem brethren. Second, it's a lot harder to teach word problems. It's easy to teach simple, repeatable instructions. Perhaps not easy all the time, but it's easier to teach simple, repeatable instructions. Things like formulas or step-by-step guides. Anything like that where it's like, do what I did, do what I did, do what I did. That sort of thing is pretty easy because you can just, follow the monkey, right? Monkey see, monkey do. You do what they led and, it works out. But with word problems, you have to teach creativity. You have to teach an ability to understand what's going on. You have to really teach analyzing a whole bunch of things at once and understanding stuff. As opposed to just teaching follow a method, you have to teach how to understand, how to think. That's a much bigger task than just, teaching a few quick instructions. So often, sadly, they're overlooked because it's easier to teach to that, and a lot of education is based on taking standardized tests. So we wind up seeing, us teaching to standardized tests as opposed to teaching to a larger scale of thinking and understanding, which is the sort of stuff that's absolutely necessary if we're going to do well on word problems. Don't let this make you be worried. Don't despair. You can learn how to do them. So just because they are a little bit harder and you don't get as much learning about them usually, doesn't mean you can't get great at them. You can get great at doing word problems. It's just going to take some thought, some imagination, and patience. Like everything else, it's going to be a skill that you can practice. You just need to practice this skill. So in this case, if, for example, your teacher doesn't assign you many word problems, it might be a good idea to work an extra word problem out of your book. Make sure it's one of the problems, because most textbooks, most math textbooks have, answers to the odd exercises or sometimes the even exercise in the back. So choose the ones that you have the answer to but wasn't assigned to you, so you get the chance to have some extra experience with word problems. So if you know that you have difficulty with word problems, you have to focus on it, you have to work on it a little bit extra. I know, I'm asking for you to do more, but there's pretty much no other way to get better at something. You get better at things because you practice, not because you just want to be better at them. So word problems are a skill you can practice, and it's a skill you can definitely improve, but you do have to practice it if you want to improve. But if you practice, you'll definitely get better, so consider that. If you have a lot of difficulty with word problems, just start tackling some easier word problems, work your way up to medium ones, and work your way up to hard ones, and just sort of do that in the background as you're working on pre-calculus. It'll be a really useful skill that will really help you in a lot of things down the road, not just math even, all sorts of stuff. Why should we care about word problems? While word problems may be difficult, they're also incredibly important. In some way, they're the point of math. Word problems turn math into something more than a meaningless series of exercises, as opposed to just solving one equation after another where it's just meaningless symbols. Word problems ground what we're doing. They give it context. They make the math mean something, which can make it sometimes beautiful and usually important to what we're doing. When we use math and science, we can better understand and appreciate our universe, right? It's through math that we can have physics sort of be able to turn into equations that we can describe our world with. It's through math that we can figure out specific things in chemistry and talk about quantities. It's through math that we can do statistics and biology and sociology. It's through math that allows us to understand the world around us. When we use it in engineering, that allows us to build amazing feats of, human ingenuity. It allows us to build huge bridges. It allows us to build, giant dams, skyscrapers. It lets us build devices like phones that fit in the size of your hand. I mean, phones, well, yeah, I meant computers is actually what I'm going to say, because most, smartphones these days are becoming even more powerful and more powerful. The incredible miniaturization of technology, what we have right now, the fact that I can be teaching you when I am in a totally different place and different time than you when you're watching it right now. Engineering, math has been put in all the engineering, in the computer stuff, in all of the, when we're building things, we need math for us to be able to make all these things. Math runs all of the technology that we have. At heart, technology is based on what we've been able to figure out in math. In many ways, it is applied math through other things. And if we use math just on its own, we can find deep truths about the nature of logic and knowledge, right? Geometry, when you were studying geometry, it's all just mathematical ideas. They have applicability in the real world, but they're also just kind of beautiful, interesting ideas. I've studied a lot of math, and I think there's some really, really cool things that you can see in math that are just purely ideas in math. But to describe them, we need words. Just a bunch of symbols isn't going to do it. Without language to connect math to these ideas, these really deep, interesting ideas, we've just got symbols. So we need language to be able to give us a deeper context, to ground what we're doing with our math. It's through word problems that we find value in math. Word problems are a connection between wanting to actually do things and learn things and this interesting symbolic language that lets us solve stuff. Word problems are the point of connection between wanting to know stuff and being able to solve things. They're really, really important for that reason. It is in many ways, word problems is what gives us knowledge. Now, not everyone's going to be convinced by my impassioned appeal to the inherent value of beauty and knowledge, right? I think that wanting to learn and the fact that learning is an amazing, really cool thing, that's a great reason to learn in and of itself. But if you'd like a more material reason, grades, right? You can get an A, and you can possibly even get a B, but you're never going to be able to achieve the highest marks in a math class if you don't understand word problems. To do your best in class, you need to be able to solve word problems. Every math is going to include, or at least really should include, some word problems, so it's important that you know how to approach them. With time and practice, you can understand them better and you can improve your grades. Remember what I was saying before, if you practice this stuff, you'll be able to improve at it. And it's not just math class, right? Any standardized test, like if you're going to take the SAT because you're interested in applying to college, or if you're currently in college and one day you want to take the GRE so that you can apply to grad school, they're going to use word problems in there as well. Pretty much any test that you'll take anywhere will have some word problem ideas going in it, so you want the ability to solve problems like that. Being able to solve word problems is crucial in a lot of situations. Also, if you want to do anything like engineer and build stuff, or do science, or do anything that is really like hard scientific connections or is really analyzing and measuring the world around us, you're going to need to understand math. So lots of really good reasons to understand math in just a material kind of benefit to us way. Finally, there's always that gem of an excuse. I'm never going to use this in real life, right? I know that you might say it's useful in science, but when am I ever going to use, partial fraction decomposition, which you'll learn about later? Why am I going to, I'm never going to use this in real life later on, so why should I learn it now? Is that true? I'm never going to use this in real life? Yeah, honestly, you're probably right. there's a very good chance that the things you will learn in this course, or any math course, will never be the sort of thing that you get paid for doing later in life. You will not be having to analyze functions, and that's going to be what gets you your paycheck every day. That's not the point. That's not the point of learning this stuff. You're not in school to learn the things that you're going to use later in life. You're not in school just to learn those things that are going to get you a paycheck later in life. You're there in school to learn how to learn. Think about this. Musicians do not play scales at concerts. Boxers do not fight punching bags in the ring, and surgeons do not operate on cadavers. But the practice that they get by doing each of those things is absolutely necessary to them being able to perform well later in life. So you might not wind up using this stuff immediately in real life, or you might never use it in real life, whatever that means. But what you're getting now is you're getting practice. Whatever you do later in life, you are going to need to learn new things over and over. So much of any interesting job, so much of whatever you do later in life is going to be learning new things and getting good at those new skills. School is your chance to practice this process. This skill of being able to learn something, get good at it, and use it. This skill is what you're learning right now, and it is absolutely necessary if you want a job that pays well, is interesting, or is enjoyable. And if you want one that is well-paying, interesting, and enjoyable, you are definitely going to have to be able to learn lots of things quickly on the fly and do whatever you need. You need the ability to adapt, the ability to learn many things and operate in many conditions. The way that you do that is you practice it now. You do not get better by just wishing you were going to be better. You get better by practicing it. School, learning, is your chance to practice the learning that you will need for the rest of your life. If you do not practice it now because you're not going to use those things, yes, you are technically right, but that's like saying, I'm not going to drive this car later in life, I'm going to drive some other car, so I won't practice driving this first car, right? To be able to drive that second car, you're going to have learned how to drive a car somewhere. So you can't skip out on learning how to drive the first car. Even though there's going to be some differences between the two cars, right? They might be completely different cars, but there's a lot of parallels here. It's going to be very similar driving one car or the other. It may be hard to see right now, but please trust me on this. I'm being as truthful as this is incredibly just like from the bottom of my heart. Put effort into learning now. The process of learning is going to give you skills that you will use for the rest of your life. It can be difficult to see how valuable those skills are to you now, but trust me, in 5, 10 years, when you look back down the road, you're going to be so thankful that you took the time and effort to really understand what you were doing, to go through all that practice of learning, because those skills of being able to learn quickly and do well and understand things, they're going to make the rest of your life so much better and so much easier. It's really important. All right, so moving on to actually solving word problems. They're so darn important, so we really want to be able to solve them, right? Now, as we discussed, there's this problem that we can't just solve all word problems with one method, but luckily there are some general guidelines that will help us work on them. So we're now going to see a 4-step process for approaching word problems. If you follow this method, you'll have clear, concrete tasks that you can accomplish at every step. Now, creativity and thought, they're still going to be absolutely necessary, but these guidelines can be used on virtually any problem that you encounter. So, really useful thing here. Let's look at it. Very first step, you need to understand the problem. Begin by figuring out what the problem is asking about. You don't have to solve anything right now. You don't even have to figure out exactly what you're looking for, but you need to figure out what the problem is asking about. You just want to have some idea of what's going on. What's the general thing that's happening here, right? Many word problems are going to unfold like a story in some way. So you just want to understand, what is this story telling me? Now, this step may seem obvious. Like, everybody's gonna be like, well, of course I have to understand the problem. But so many people gloss over it and they just try to hop right into solving the problem. But you need to understand it first. How can you solve something if you don't even know what's going on? You have to know what's happening in the problem, what the problem is about, what the ideas going on are before you're going to be able to have any chance of actually solving it. So first, just get a sense of what's going on. Once you have that, second, what are you looking for? Set up your variables. What are you looking for? Once you know what's happening in the problem, you want to figure out, what are you trying to find? What are the ideas that are central here that you need to be able to work out this problem? Now, almost always, especially for the next few years while you're in, before you get into really advanced math classes, if you continue to study math in college, so pre-calculus, calculus, even the next couple years, this will take the form of setting up variables. You'll set up variables. Define any variable that the problem asks for. You might also need to define other variables, such as values that are talked about but never explicitly given. Now, I want to make absolutely sure you write down what each variable means. I really want to make sure you do this. So I'm not kidding. Until you are extraordinarily comfortable with word problems, you should be literally writing out a little reminder of what each variable means. So for example, if you had a problem where you had to talk about some number of tables, then you might say, just before you start it, t equals number of tables, right? T equals number of tables. And then you also might have to talk about chairs in the problem, so c equals number of chairs. And that's enough right there. But very often students will be working on it and they'll sort of forget what the letter meant or what is really there. This is a way of anchoring your work so you know what you're searching for, what these ideas are about. And by writing it down, it'll make it that much easier to work on the rest of the problem. So really, really, really write down what the variable means. It should be completely obvious to you, either because you'll have a picture, which we'll talk about later, or because you've literally written out what the variable means. That way you can't forget it while you're in the middle of working on the problem and get confused. So you set up what you're looking for at this point. What you're looking for, what's unknown, what's going to help you get to figuring out the answer. Third, you set up relationships. You want to figure out what the problem is telling you about what you're looking for. What is the problem telling you about what you're looking for? So you're trying to solve for something at this point, which you figured out from number 1. And you know the sort of ideas that you're looking for. That was number 2. So now you need to figure out what is the problem telling you about those things that you're looking for, those variables if we're doing a math problem. Use what you know. Use what the problem gave you to set up relationships between your unknowns and whatever information the problem gives you. Now, in math class, especially for the next few years, once again, this will usually take up the form of making equations. This is what it's normally going to boil down to, is you'll be making equations. You'll set up equations involving your unknown variable or variables and whatever else you know from how the problem was set up. The problem will tell you some information and you'll use that information to build equations. And if it's something that's not specifically a math problem or a more general form of math problem, you might be just using it to set up things of what you know and what you can rely on as you start to work through it. Sometimes, as you're working out on these equations, you'll realize you have more unknowns than you originally thought. That's perfectly fine. Just make up new variables at this point. You realize, oh, to use this idea, I need to also have this new variable introduced. Introduce a new variable. Hop back to step number 2, make a new variable, write down what it means, and then plug it into the equation where it's going to go in. Figure out the equations that will involve that new variable that you realize you need to use. Finally, once you understand what the problem is about, you know what you're looking for, and you have all of your relationships, equations, set up, you're ready to solve it. Normally, in many ways, this is going to actually be the easiest part because it's just like doing any other exercise now. You've got equations to solve, right? You're looking to solve for something and you've got equations. It's just going to be a matter of doing the math that you've been doing in every other section, in every other part of the section that you're working on. You'll normally have many exercises and they'll only finally culminate in some word problems. So it's just like doing all the exercises you've been doing before. It's just it sort of had this framing of how we get to those equations, how we get to doing the exercise. So you have some equations to solve or something like that. Roll up your sleeves and work on it like a normal non-word problem. And as a general rule of thumb, so to solve a problem, you need as many relationships as you have unknown. So for example, if you need to find out 3 variables, you have to find out 3 variables, then you'll have to have 3 equations or more that relate the 3 variables together. So you'll need the same number of relationships, same number of equations as the pieces of information you're trying to find out. So it's sort of like each equation is a key that you can fit into an unknown lock. Each equation is a piece of knowledge that you can use to shine a light on some unknown thing. In summary, complex problems can be approached by first understanding what you're working on, then figuring out what you are looking to find, figure out what you want to know, what you need to know. Third, you work out relationships. How do the things that you know already from the problem and the things that you're looking to find, how are they connected to each other? And then finally, you put it all together and you get the answer. So that's our basic summary of method. Now, it may seem surprising, but this method can actually be applied to pretty much any problem, any issue you have, not just math. This is such a general tool for approaching complex ideas that you can use it for pretty much anything that you're trying to figure out a way to solve an issue. You're probably used to doing this in all sorts of situations already. It's just a good way to approach problem solving in general. And so let's actually see two examples that are not connected to math, just so we can get an idea of how we solve problems on a general scale. So consider these two situations. First situation, your car is making weird noises when you drive. And in the second situation, your friend suddenly stops talking to you one day, right? Very different things, but both issues that you'd want to deal with. So to begin with, our first thing is we understand what's going on. Your car is making weird noises when you drive. Well, if my car is making weird noises, there's probably some sort of issue going on. And so now you also have sort of like, in a word problem in math, we're going to have a more specific be told what to do. In real life, our issues are normally more amorphous, more uncertain in what we need to do to get to the right thing. But with this case, let's say, we figure out our car is a problem. We need to figure out what that problem is, and then we need to fix it. Now, let's say in this world, we don't want to spend the money on taking it to a mechanic. So that means we have to be the one to figure it out, and we have to be the one to fix the problem. So your car is making weird noises when you drive means that what we need to do here, our understanding of it is we need to figure out what the problem is, and then we need to fix it. That's what our objective is, fix the problem. In the version where we're talking about our friend who stops talking to us, what we want to do now is we ask ourselves, well, do I care about this friend enough to want them to still be my friend? And we're going to assume, yeah, they are actually your friend. You want them to be friendly again. But this is one of our things where we're trying to understand the problem. We actually have to understand and think about what it is. How does it connect to the rest of what's going on? Right? If your friend suddenly stops talking to you one day, but you actually just realized you don't actually like them at all, then heck, they're no longer a friend. Just make them no longer your friend. But in this case, we're saying, yeah, our objective is to get our friend to be friendly again. We want them to actually be our friend, not just be this person who won't talk to us. All right, now we've got our objectives in mind. Now we can figure out, what do I need to know? What are the things that I don't know that will help me get to that objective? Second step, in the car example again, if our car is making weird noises and it's got some sort of problem as our assumption, we want to figure out what is making that noise, right? What's making the noise? We also want to figure out, is the thing that is causing the noise the result of some other issue? And if there is some other root issue, is it damaged anything in the car? And then finally, how can we fix any and all damage? Now really, this is the only thing that matters, right? We don't really care. In truth, if some genie appeared out of nowhere and said, I will fix your car for, just because I'm a nice guy, we'd go, heck yes, genie, fix that car. Yay, right? And they'd fix our car. So really, if we could somehow get a genie to show up here at the end, we wouldn't need to know the answer to those first three things. But hey, it's real life. It's likely going to be the case that these first three issues, these first three unknowns, would really help us to fix the damage, right? If we can figure out what's causing the noise, if we can figure out if there's an issue that's making that noise, and we can figure out that issue has damaged anything, those are all things that are going to help us fix the car, make it stop making that noise. So while our final unknown is the how do we make it better, we really want to know other things on the way if we're ever going to be able to figure out how to make it better. In the version where we're looking at our friend, we might want to know, why is our friend not talking to us, right? Why is our friend not talking to you? And then what has happened recently would probably be a good way to get a sense of why they aren't talking to you. And finally, what is the best method to make them friendly? Once again, we might actually not care about all of the other stuff, right? All the first two things, we'd probably be curious why our friend isn't talking to you. But once again, if that genie appeared and was like, hey, I'll make your friend be your friend again, no problem, I'm a nice guy, we'd be like, thanks, genie, you're the best. Right? This genie would be pretty awesome and they'd make our friendship better. But in real life, we have to deal with our problems. We have to make things better. So we have to figure out how to solve the problem, right? We don't have some genie who's just going to do it for us. So we have to figure out how to solve it. So while the only thing we really want to know is this final idea, to be able to get to the point where we can figure out that final idea, it would probably be very useful to know why our friend isn't talking to us and what has happened recently that frames what's going on right now. So this is an idea of how we set up what are the unknowns that would help me answer that original question. For car troubles, if we want to answer what those unknowns are, get a sense of those things, there's a bunch of things we could do. We could look under the hood. We could get a service manual for the car. A service manual tells us how a car is put together, how that car is put together. We could talk to friends and family who know cars well. We might research the problem online or anything else we can think of that would tell us more about what's going on with the car, right? These would help us answer the unknown questions of what's wrong, what's the issue, has there been any damage, and how do we fix whatever damage it is and fix the underlying issue. With the friend, we want to think about what happened to your friend recently. We want to think about your recent behavior to your friend. We want to ask our other friends if they know what is wrong. Perhaps they have some information that we're unaware of right now. We want to pay attention to how our friend is acting when we're not around or when we're sort of like not interacting with them directly. That will give us some sense of what's going on and be able to help us understand the situation. And we can use all those pieces of information to help us figure out how to make them friendly again, to make things better. With all this information, we now just figure out what's wrong with the car and what we need to do to fix the issue. And then we do it. In the friend version, we use all this information to figure out what would put our friend in a good mood and be friendly towards us again. And we do it, right? We use the information to give us a bunch of stuff that we can now do to reach our objective. That's what's going on in complex problem solving just generally all the time. We figure out what the problem is, we figure out what we need to know to deal with that problem, we figure out how we can answer those things that we need to know, and then we use all that information to get what we want. Math-specific method, so that's really great for any complex problem, and it can be used on anything at all that you need to solve. But what about what we're going to see exactly in math? This general method is great, but let's see what we're going to use pretty much in the next couple years. So let's look at the specific approach we'll be using. So once again, we understand what the problem is about, right? We want to just get a sense of what's going on. Then we set up and name variables. Variables represent our unknowns, the things that we're going to need and have to have a handle on to be able to answer the problem. Then we set up equations. We use the information that's given to us in the problem statement to get us the equations that we need to be able to answer the question. And then finally, we've got equations. We solve for that answer. We've got equations, we know what we're looking for because we understood the problem in the beginning. We just work it all out, boom, we get an answer. There are going to be a few word problems, probably around 5 to 10%, depends. But these are going to be mostly concept questions and proofs. So there are a few word problems that won't use this exact formula of understand, variables, equations, solve. Right? That's our formula in general when we're approaching word problems. But sometimes we're going to have to prove things, or sometimes it's asking a general concept question of, is this true? Is this false? Why does this happen? And in those situations, we won't be able to use this exact method, but we can fall back on that more general method where we just think in sort of large-scale, complex terms. Tips. Let's start talking about tips that help us improve the efficacy of this method. So we understand how the method works now. It's go through and understand, set up the things that you're looking for, your variables, set up what you know, your equations, and then finally solve it. Put it all together and solve it. So here are some tips that will help us use this method. First, draw pictures. This is probably the single most useful tip in all of this. Draw pictures. It may not be possible for every problem. Some problems are going to be completely abstract and you won't be able to do this. But when you can, it's going to help massively. Basically, if a problem is asking about geometry, shapes, or something that is like physically happening, if something is a real world thing that we can imagine, it's really useful to draw a picture. If the problem doesn't give you a picture from the bat right off, draw it yourself. Just draw a picture. And don't worry about making the picture look nice. You just want something that you can sketch in a few seconds and that makes sense to you. Cars can become boxes, people can become little stick figures, you can change things to dots and just straight lines. You don't have to draw like an entire road. If we're talking about a road, it's just enough to have a straight line, right? You just want something that you can use as a reference point so that you can see it in your mind's eye. It's not absolutely necessary to do this, but a visual representation of a problem can help so much. When you're not sure how something works or what to do, sometimes a quick sketch so we can see what's going on, sometimes they can help clear things up so much. It can be really, really useful. Drawing pictures is a great way to approach word problems. It really helps us understand it, helps us figure out what we're looking for, helps us set up our equations, and it can help us solve it. Really, really useful stuff. Next tip, breaking things into pieces. Imagine you have a plate in your hands. You drop it and it breaks into many pieces. If you collect all the pieces and you put them back together, you'll have the plate again, right? And if you pull apart the rebuilt plate, you'll have all the pieces again. So you can take something into the pieces that make it up and you can put it back together to make the whole. The whole is made out of its parts and the parts make up the whole. The sum of the parts equals the whole equals the sum of the parts. That's what this idea is expressed by. It's a simple idea, but it's important and it comes up in math a lot. Consider this problem right here. If we want to figure out what the area of the shaded area is, we want to figure out how much shaded area there is. By breaking this figure into its pieces, we can figure out how to do this, right? We see, oh, that shaded part and that semicircle, they come together to form a square. Well, I know what the square is, I can figure out what the semicircle is, and so I can use that information to figure out the shaded area. You can break things into its pieces. And this will normally be applied to geometrical things where we're talking about shapes and objects, but once in a while it'll actually be applied to mathematical things where it's just in terms of like letters and stuff, and we'll actually break stuff into its pieces then and use each of the pieces on its own. We'll see that stuff later down the road potentially, and we'll talk about it then if it happens. But normally you're going to wind up seeing it in picture stuff where we're dealing with shapes and geometry, things like that. But it's a really useful idea. It comes up in a lot of different places. Next, try out hypothetical numbers. Sometimes it can be hard to figure out what's going on in a problem because we're not working with numbers. We're really good at working with numbers because we've been doing it for like a long time at this point, right? So you can try plugging in hypothetical numbers to help you understand what's going on. Now, if you try a hypothetical number, make sure you try out numbers that follow the rules set in your problem, right? If your problem says that the number is even, you want to make sure whatever hypothetical number you use is something like 2, 4, 6, 8, so that you're following the rules that they tell you, so that you can go along that path. This is a great way to test the equations you set up, right? We can set up an equation and be like, well, this should tell me like how much money the company made. And what we do is we plug in some numbers and say, well, what if they made like 10 things, 10 widgets? Well, we could probably figure out what it should be for 10 widgets, and so we can make sure that our equation is spitting out the same thing that we know 10 widgets should make them in terms of money. And so we can make sure, yeah, our equation, it seems to be checking out. It's working when I use it on simple numbers that I can easily understand. So now we can, it's up and running, and we can use it on variables and trust it. So if you have difficulty setting up equations, try plugging in hypothetical numbers to understand what's going on in there. It's easy to make mistakes when you're setting up equations, so check them afterwards by plugging in hypothetical numbers if you're not sure. You can plug in a number that you understand what should happen there, and then you'll see, oh yeah, that makes sense. And we'll see some examples when we work on the examples part of this lesson. If things don't work out with your hypothetical number, you know you made an error in your equation, or possibly an error in your hypothetical number, and there's something you need to go back and work on, make sure you fix it before you move on and try to solve it. Student logic. This is an interesting idea. The hardest part often can be figuring out what relationships are going on, right? But you've got a secret weapon. You're a student. What I mean by this is that you can use student logic. You can be pretty much certain that whatever your problem is going to be about, it's going to use what you're currently learning, right? If you are a student, they're not going to have you do something that you haven't learned, and they're probably mainly going to be focusing on the stuff that you've been working on. So whatever you're currently learning is exactly what you'll probably use to set up the relationships. For example, if you're currently studying parabolas, you know the problem can almost certainly be solved by using something that you learn about parabolas. So you'll set up your word problem and then you go, oh right, what do I know about parabolas? Oh, the top of a parabola happens at this equation, and so you'll see, would that be useful here? And it probably will be. Try to figure out how the problem is related to what you've recently been studying. How is this connected to what you've been working on in this section, in this lesson, in this chapter? And then use those ideas to help you set up the equations. You don't have to normally worry about things that are completely unrelated to what you've just been learning, because your teacher is normally trying to teach you the stuff that you've been working on, so they're going to be using those ideas in the word problems as well. Jump in. This is a good suggestion. You don't want to just get paralyzed. Working on word problems can sometimes freeze you up and you're like, I don't know what to do. I don't know what to do. So just calm down, try something. You're not sure where to start. You don't know exactly what you're looking for. You don't see how to solve it, so you freak out. But instead, that's okay. That happens to everyone. Instead, toss in something. Try to do something. If you can't set up the equation right the first time, that's okay. If you pick the wrong variable, that's okay. If you plug in the wrong hypothetical number, that's okay. You're probably going to learn from your mistake. Normally, by making a mistake, we go, oh, well, that didn't work. Oh, but because that didn't work, this other thing would work, and then you're right on the way to doing it. As long as you pay attention to what you're doing and you think about what makes sense and what doesn't make sense, and you're double checking your work and thinking, is this sane? Is this a reasonable thing to be doing? You're normally going to see where you went wrong. And by seeing where you went wrong, you can realize what you need to do in the problem. The fastest way you can learn is often by just making a mistake. So reach in, get your hands dirty. It's okay if things go wrong at first, because eventually they'll work out. If you just stand back and keep thinking, I don't know how to do this, I don't know how to do this, yeah, you're right. You're not going to know how to do it because you're just saying one thing, you're just, you're pulled back. You need to try something. Trying something is almost always going to work better than doing nothing. So just jump in, get started if you get stuck. All right, let's look at some examples. So, 4-part method. First, understand. 2, set up variables. 3, set up equations. 4, solve the thing. So first off, we need to understand this. So number one, we read through it. Sally has a job selling cars. Her monthly base pay is $2,000 along with a 1.7% commission on all the cars she sells. If she earned $5,315 in March, what was the total cost of the cars she sold in March? So the first thing we have to do is we have to understand what's happening here. Okay, so Sally has a job selling cars. Check, makes sense. She gets paid some base pay. Okay, she gets paid some amount and then, along with, so she gets paid $2,000 plus some other thing, this commission. Now we might go, I don't know what a commission means. So what do? We look it up, right? You toss the word commission into an internet search or you look up commission in a dictionary. It would probably be a good first step. If you don't know what the word commission is, you look it up. We look up commission and we find out that it is normally a percentage fee that you get for selling something. So if somebody has like a 10% commission, if they sell $100 of stuff, they personally get $10 back. So a commission is a way of making a profit off of what you sell to other people. A salesman gets a commission on their sales generally to encourage them to sell more. So she gets a 1.7% commission. 1.7% of whatever she sells, she gets back. Okay, so she gets $2,000 plus 1.7% of the amount of the cars that she sold in the month. Cool. If she earns $5,315 in March, what was the total cost of the car she sold in March? Oh, so we have a piece of information about March. We're looking to know about how much cost of that. So we're looking for a connection between how we know her money breaks down and what the cost of those cars must have been. All right, so number one, check. We understand what it's about. So number two, what are the things that we need to know? Well, P, we want to be able to talk about her pay, right? How much does she get paid? So we want to have some way of being able to talk about how does that vary based on her commission. So how about we make C equals not commission, but the cost of cars sold. So this is the amount of money she makes off of the cars she sells. So now let's figure out a way of being able to make this $2,000 along with 1.7% commission into something. So she gets $2,000, right? So number two, done. We figured out the things that we need to talk about. Her pay and the amount of the cars that are sold. The two variables that we're really looking at. Number three, we set up equations. So we want to have some way of being able to talk about her pay, right? $2,000 plus 1.7% of the cost those cars are sold. So how does that work out? We might go, well, I don't really remember how percent works. So let's test some stuff, right? We know 10% of 100 should wind up being 10. We know that 5% of 100 should wind up being 5. We know that 1% of 100 should wind up being 1. So we might go, oh, right, you move the decimal 2 over and then you multiply. 0.017. Let's check and make sure that makes sense. If she sold a $100 car, a cheap car, but hey, if she were to sell $100, 1.7% of 100 would be $1 and 0.70 cents. So she should make $1.70. 0.017, let's check that out. 0.017 times 100 would wind up being, we move the decimal 2 over, 2 over, we get 1.7 or 170, which would be $1.70. Check. Makes sense. So 0.017 times the cost of the cars sold is equal to the amount that she gets paid in any given month. Now, what month are we looking at specifically? March. So we know that P in this case is equal to $5,315. So we take this information, we plug it in here, we have 2,000 plus 0.017 times the cost of the cars equals 5,315. From here, it's just step number 4. We set up our equations, we know how the things interact, we know all this, now we've just got an equation to solve, right? We want to know C. C is what we're looking for. It asks what was the total cost. So we're looking for C equals question mark. So we just solve for what is C got to be. Subtract 2,000 from both sides. We get 0.017 equals 3,315. Oh, whoops, 0.017C. And then we divide both sides by 0.017. So we get C equals 3,315 over C, which, Lord, said the wrong thing. 3,315 divided by 0.017, We plug that into a calculator to make it easy for us, and we get $195,000. So she makes $195,000 in terms of what she sells, which brings her a commission of $3,315, so a total pay of $5,315. The total cost of all the cars she sold was $195,000. Great. Example 2. First thing we want to do, we want to understand what is going on. So very first thing, we've got a semicircle of radius 8 inscribed inside of a rectangle. So we might go, what's a semicircle? Oh, well, we look at the picture. Yeah, a semicircle is half of a circle, right? Semi, half a circle. Makes sense. So it's radius 8 from center to edge is 8. Great. It's inside of a rectangle, so it's inscribed. We see exactly what it looks like. What is the area of the shaded portion? So we want to figure out how much is the shade in here. So we understand what we're looking for. We've got half a circle held inside of a rectangle, so it barely touches the edges, and we're looking to figure out what's the part that isn't the circle, but is still contained in the rectangle. What's that shaded portion? Great. So number 1, done. Number 2, what would allow us to know this? Well, if we knew what the area of the rectangle was, so area of rectangle. If we know what the S for the shaded area, and if we knew the circle's area, we'd be in pretty good shape to be able to figure this out. So number 2, those are the 3 things we're looking for. R equals the area of the rectangle, capital R. S equals the shaded area. C equals the circle's area. Great. So number 3, we start looking for some equations. So can we figure out what the area of a rectangle is? We go, oh yeah, it's length times width. So R equals length times width. So now let's go back and let's look at our picture. Well, if this is 8 from center to edge, well, hey, look, over here is the edge of the circle. So this is 8. Over here is the edge of the circle, so this is 8. So the entire length is 16. Vertically, we've got, if we go from here and we go directly up, then this is 8 here, so it must be 8 on this side as well, right? So we've got length times width. We know that is 16 times 8, which comes out to be 128. So now we know what the area of the rectangle is. Great. What about the area of the shaded area? Do we know what that is? No, that's what we're looking for. It's what the problem asked, so that's our question mark. It's our unknown. C, can we figure out what is the semi, and let me write this out, it's the semicircle, not the circle, because it's half a circle. So C equals the semicircle's area. Now we go, well, what is the area for a circle, right? If I knew the area for a circle or a semicircle, I'd be good. Well, we probably remember the area for a circle is pi r squared. And even if we don't remember what the area for a circle is, we go, I've learned this before. Let's type it into an internet search, right? You type in area of circle, boom, you've got it right there. Or if you've got a math book, you can possibly look in the cover and it will already have that formula right there. So area of a circle is pi r squared. So circle equals pi r squared. So area for a circle is equal to pi r squared. Now notice this is r, not this capital R. The area of our rectangle is very different than r. What is little r here? We look once again, try to remember what is the, oh right, it's the radius of the circle, from the center of the circle out. So the radius of our circle, hey, it's 8, center of circle out. Now there's one difference between the area of a circle and the area of our semicircle. What's a semicircle? It's half of a circle. So it is 1/2 times pi r squared. So 1/2 times pi times 8 squared equals 1/2 times pi times 8 squared. 8 squared is 64, so that gets us 32 pi. Now that's that's 2 pieces of information, right? We know r equals 128, we know c equals 32 pi, but we're still looking for this other thing, right? We have 3 unknowns start with r, s, and c, and we've got 2 pieces of information. So we need some way to connect s to r and c. Well, we look at the picture and we go, oh, hey, the area of the rectangle, the shaded area, the semicircle, they're all connected, right? The area of the rectangle contains both of the other guys put together. So it's s plus c. So at this point, we're ready to go on to step 4. We've got all of our equations set up. Step 4, r equals s plus c. We've got numbers, so let's get s on its lonesome because that's what we're looking to solve. So r minus c equals S, the area of the shaded area, is equal to the rectangle's area minus the area of the semicircle. So we plug in the area for the rectangle, that's 128, minus the area for the semicircle, that's 32 pi, and that's equal to our shaded area, and that is our answer because there's no way to combine 32 pi and 128. They speak different languages. If we want, we could plug it into a calculator and get 32 times 3.14 and then get something, but 128 minus 32 pi, that's a great answer. There we are. Next example. Tobias has precisely 17 coins in his pocket, so first thing we're doing is we're understanding what's going on. So number one, Tobias, he's got some coins in his pocket. Makes sense. 17, cool. Coins come in 3 types, okay? So he's got 3 different coin types: quarters, nickels, and pennies. Now, if we didn't remember, we'd go, oh, what's a quarter? We look it up. Quarter is 25 cents. What's a nickel? 5 cents. What's a penny? 1 cent. Cool. He has a total of $2.17 in coins. If he has 2 pennies, how many quarters does he have? So let's see, so everything here makes sense. Kid has some change in his pocket. They come in 3 different types of coins that make up that change, and he has a total amount of money, and now we want to find out what the specific number of quarters are. So what might be useful to know? First, we're certainly going to need to know what is the number of quarters. That's our very first thing. So here's step 2. First unknown that we definitely have to figure out is number of quarters. Well, we'll probably also want to know how many nickels and how many pennies he has because they're connected to the other pieces of information right here. N equals number of nickels. And finally, P equals number of pennies. Those little reminders serve us to understand what's going on as we work through. Now, number 3, how can we connect these ideas together? So now we notice, well, how can I talk about the number of coins in his pocket? Well, I know what the number of quarters is, and I know what the number of nickels is, I know what the number of pennies is. Do I literally know what they are? No, but I have names for them. So we can talk about, well, how can we say how many coins he has in terms of these variables? Well, he's going to have his number of quarters plus his number of nickels plus his number of pennies should describe the amount of coins, the number of coins in his pocket. Let's check and make sure. Let's do a real quick check. What if he had 2 quarters, 1 nickel, and 1 penny? Then 2 quarters for Q, 1 nickel, and 1 penny, P. So 2 plus 1 plus 1, 4 coins. And yeah, he would have 4 coins. Great, makes sense. In this case, we were told that he had 17 coins, so Q plus N plus P equals 17. What else were we told? We were also told that $2.17. Oh, so how can we figure out how much money he has? Well, if he had 2 quarters, that would be 50 cents. So let's make things easy, and let's, in fact, instead of talking in terms of dollars, we'll talk about 217 cents, right? So we'll think just in terms of cents. If he has 1 quarter, how many cents does he have? 25. If he has 2 quarters, he has 50 cents. Oh, it's 25 times the number of quarters. So 25 times Q is how much money, how many cents he has from quarters. What about nickels? Well, 5 times the number of nickels. Let's check and make sure. 3 nickels would be 15 cents. 5 times 3 would be 15. Hey, checks out. So 5 times nickels plus, what if we had pennies? Well, what number would we multiply by pennies? Oh, pennies would just be by 1, so it's just the number of pennies. So that's going to be the amount of money in his pocket. In this case, we know how many cents he has. He has 217 cents. $2.17 is the same thing as 217 cents. We are thinking about this in terms of cents. That way we just don't have decimal numbers. Finally, do we have any other information? Because currently we have 3 unknowns, 3 relationships. Ah, yes, he has 2 pennies, right? So we know right off the bat, P equals 2. 3 pieces of information, 3 unknowns, we're good to go. Check. So number 4, we start working things out. Well, we're going to have to somehow use P equals 2 in one of these 2. So let's plug it into this one first. So Q plus N plus 2 equals 17. So that means Q plus N equals 17, or let's go with N. We'll solve for N because we want to work out Q over here, so we'll plug it in here and we can keep working up through substitution. N equals 17 minus Q. Great. We take that information, we plug it in over here. So 25Q plus 5 quantity, remember we have to substitute with quantities, 17 minus Q plus P equals 217. Hey, do we know what P is? Yeah, we sure know what P is. P is just 2. So 25Q will distribute that 5 plus 5 times 17. 5 times 17 is 70, whoops, oh, hup, Made a mistake here. Sorry about that. Hopefully you guys caught that and were thinking, what are you doing? Q plus N, we subtracted 2 here. A good example of why we have to make sure we do the exact same thing on both sides. 15, 15. So this shouldn't be 17 minus Q over here. It should be 15 minus Q over here. Great. So 25Q plus 5 times 15 minus Q. We get 75 minus 5Q. And then we'll also subtract 2 right now just to get rid of it. So we'll get equals 215. Great, 25Q plus 75 minus 5Q. Let's consolidate that. We'll get 20Q, and then let's also move the 75 over to the other side, minus 75, minus 75. So we get 20Q equals 215 minus 75 is 140. So Q is equal to 7. The number of quarters he has in his pocket must be 7 quarters because we were able to work things out from those original equations. And if we wanted to figure out what the number of nickels he had was, we could just plug it right here and we'd get, oh, he must also have 8 nickels. So if N equals 8 and P equals 2, N equals 8, P equals 2, Q equals 7, we can do a really easy check. Is 7 times 25 plus 5 times 8 plus 2 equal to 217? Yes, it winds up being that that does check out if we multiply the number, what the quarters should be worth and that, and 7 plus 8 plus 2, that equals 17. So everything checks out. Our answer makes sense. Q equals 7. Great. Final example, we've got a tank for holding water. Well, first step we need to do, we need to understand what's going on. Tank for holding water is shaped like a circular cone with its point towards the ground. What does that look like? Oh, yeah, I've got okay, yeah. So you draw something circular and then it comes to a point like a cone. Cool, makes sense. The tank is 10 feet tall and has a diameter of 6 feet at its top. So let's put that into this. So it's 10 feet tall and has a diameter that is 6 feet across. So 6 feet across. What is the volume when the tank is full? And then we've got a second part, what is the volume when the water is only 5 feet deep? So let's just start off by breaking it here and we'll answer what is the volume in the tank when it is full. So our first thing makes sense. We've got this cone full of water. We fill it up to the top. How much water is going to be in it? So second part, second idea, we want to get what we need to know here. So it seems like it'd be useful to talk about the height, right? Well, we actually know what the height is. So height, H will equal the height of the cone. And let's say D equals, we were told the diameter, so let's say the diameter. Even though these are really just going to be values, we can talk about them as if they're like that. And that seems like everything we need to know right now. So let's go and let's see, do we have a good way to relate these two things together? How can we relate the height and diameter of a cone to its volume? So we might go, well, how do I get volume of a cone? I've learned this before. They told me in geometry. Right, it's this. We remember the formula. Or maybe we don't remember the formula. Like, well, I know I've been told it. So if you've been told it, it's out there on the internet, right? Or it's in a math book. Just either crack open a math book or do a quick web search and you'll be able to find it really quickly. And you find out that the volume of a cone is equal to 1/3 times what the volume of its cylinder would have been. The volume of its cylinder would have been the area of the top, pi r squared, the circle, times the height of the cylinder. Okay, now at this point we go, wait a second, we are talking about volume. We want to know what volume is, right? So volume equals question mark. That's what we're really searching for. But did we have R show up before? No, we didn't have R show up before. So let's make a new one. R equals radius, right? So we were told some stuff here. We were told the diameter is 6 feet. So how does a radius connect to that? Well, we go, oh, right, diameter is just double the radius. Radius is half the diameter. So R equals 3, right? Halfway would just be, if the whole thing is 6, then halfway is going to be 3. So R equals 3. Our H equals, our height was 10 feet tall. So H equals 10. Now we've got only one unknown left in this equation here. V equals 1/3 times pi r squared times height. We know what the radius is. We know what the height is. Pi is just some number. 1/3 is just some number. So the only thing we're looking for is volume. Real easy. We just plug our numbers in at this point. So fourth step, just solving it. Our volume is equal to plugging in the values. 1/3 times pi times 3 squared times 10. So that's going to wind up being the 9. The third here will cancel the squaring that we've got here. So we've got pi times 3 times 10, or 30 pi, and we have to talk about it in terms of units. So if it's volume, and we've been doing feet before, it must be cubic feet. And there's our answer. All right, now what if we wanted to do this other portion of it, right? So we'll change over to a new version. Now it's nice because it's going to follow a lot of parallel ideas, so we can just use what we've already figured out. So instead of being 10 feet tall, it's only 5 feet tall, right? So the water really only comes up to here. Now if that's the case, if the diameter is 6 up here, is the diameter going to be the same down here? No, that makes no sense, right? The diameter can't be the same because it's a cone. It shrinks down the farther down we get. So if we were all the way at the bottom, the diameter would be 0. If we go all the way up to the top, it'd be 6. It makes sense that the diameter is going to be half of what it would have been before because we are now at half the height. So the diameter in the middle is 3. So that means our radius is equal to 1.5. Our height is 5. And that same formula from before, our volume formula for a cylindrical cone, still works. So volume equals 1/3 times pi r squared times height. We plug in 1/3 times pi times 1.5 squared times 5. We work that out. 1/3 times pi times 11.25 simplifies to 3.75 pi, and it's in cubic feet. And there is our answer. We're basically following the same outline we did before, so we don't have to worry about doing it step by step, because we can just work from our previous idea. We figured out how it was done in the complex way. Now it's just a matter of using new values and making sure that the values we're using are right? R changes because we're at a different place, height changes because we're at a different place, but all the relationships, they're still the same, which makes sense. We want to be thinking about it, but it makes sense that all the relationships are the same because we're still just looking to figure out what is the volume inside of this cone. It's just now a cone inside of a cone, right? Cool. All right, hope that made sense. Hope that gives you a slightly better understanding of how to approach word problems. Don't be that freaked out by them. It's just a matter of breaking it down and understanding what's going on, setting up what you're looking for, figuring out the relationships that connect what you're looking for to what you know, and then finally just solving it like a normal math problem. All right, we'll see you at educator.com later. Bye.